He'd been maintaining wind turbines for 15 years, climbing 300-foot towers, replacing worn components, keeping the massive generators spinning safely. Just another elderly technician trying to stay active in the renewable energy industry. Until catastrophic blade failures threatened to destroy an entire wind farm and endanger nearby communities. And suddenly, the quiet maintenance worker revealed why he understood rotating machinery that stumped engineering consultants. Walter Heinrich Braun was 73 years old, with steel-gray hair that remained thick despite decades of exposure to wind and weather, and piercing green eyes that could detect mechanical problems through subtle vibration changes that escaped sophisticated monitoring equipment. His calloused hands moved with practiced confidence despite arthritis, performing maintenance tasks at heights that intimidated technicians half his age, while his voice carried the methodical cadence of someone who understood that rotating machinery required respect for forces that could kill instantly if safety procedures were compromised. Welcome to the Human Stories. Before we continue this incredible tale of hidden expertise and life-saving mechanical knowledge, tell me in the comments what city you're watching from today. And if you believe stories about quiet masters deserve to be heard, hit that subscribe button. Prairie Wind Energy operated one of the largest wind farms in Nebraska, where 127 turbines generated enough clean electricity to power over 85,000 homes, while standing as monuments to America's commitment to renewable energy independence. Each turbine represented a $4 million investment in technology that converted wind energy into electrical power through rotating machinery that operated under stresses that challenged the limits of material science and mechanical engineering. Walter had worked as senior maintenance technician for 15 years, responsible for keeping turbines operational through preventive maintenance, component replacement, and emergency repairs that required working at heights where wind speeds could exceed 60 miles per hour. His duties involved climbing turbine towers that stood over 300 feet tall, accessing nacelles that housed generators weighing over 100 tons, and maintaining rotor assemblies with blades longer than football fields. The walls displayed mechanical engineering diagrams and test documentation, spanning over 4 decades of turbomachinery development, jet engine designs that had advanced commercial aviation, gas turbine systems that had improved power generation efficiency, and rotating equipment research that had contributed to everything from naval propulsion to industrial manufacturing. Bookshelves held technical references that most mechanical engineers would consider graduate-level material: turbomachinery design texts, rotating equipment failure analysis manuals, and vibration dynamics research that Walter had contributed to during his corporate career. Filing cabinets contained project documentation for rotating machinery that had shaped how America approached both military and civilian applications requiring high-performance mechanical systems. And then a secure file drawer that seemed excessive for wind turbine work were credentials that would have transformed how Nebraska's renewable energy community viewed their maintenance technician. A PhD in mechanical engineering from Purdue University, senior engineer credentials from major aerospace companies, and consulting agreements with General Electric and Pratt & Whitney that had shaped how America developed advanced turbomachinery for both commercial and defense applications. Dr. Walter Heinrich Braun, internationally recognized authority on turbomachinery design and rotating equipment failure analysis. His career had focused on developing jet engines for commercial aircraft, gas turbines for power generation, and advanced rotating equipment that operated under conditions that exceeded anything civilian applications demanded. But equally important, he'd established maintenance protocols and failure analysis techniques that prevented catastrophic mechanical failures in rotating equipment where failure could cause mass casualties. The work had taken Walter from theoretical research that advanced understanding of rotating machinery physics to operational systems that powered everything from commercial aircraft to naval vessels. His expertise had been crucial in developing the vibration analysis, material science, and maintenance procedures that governed how American industry approached rotating equipment that operated under extreme conditions. His research had contributed to major advances in turbomachinery reliability,
including the development of condition monitoring systems that could predict bearing failures weeks before they occurred, blade stress analysis techniques that prevented catastrophic rotor failures, and maintenance procedures that extended equipment life while maintaining safety margins that protected both operators and the public. Retirement in 2009 had been voluntary rather than mandatory. Walter had accumulated enough years in aerospace engineering to retire with full pension while still young enough to pursue work that didn't involve the corporate pressures and defense classification restrictions that had characterized his professional career. The wind turbine maintenance position wasn't about financial necessity. His aerospace pension provided comfortable retirement income. It was about applying turbomachinery knowledge to renewable energy rather than military applications, using rotating equipment expertise to advance clean energy rather than weapon systems, and continuing to work with sophisticated mechanical systems that challenged his technical abilities while contributing to environmental sustainability. But 41 years of turbomachinery engineering expertise doesn't disappear because someone changes from aerospace research to renewable energy maintenance, and Walter's trained understanding continued monitoring rotating equipment behavior that could affect both wind farm operations and community safety. Wednesday, September 18th started like every other maintenance day. Walter arrived at Prairie Wind Energy at 6:30 a.m., reviewed overnight performance data from the turbine monitoring systems, and prepared for another day of preventative maintenance that would keep the wind farm generating clean electricity efficiently and safely. The morning proceeded normally until 9:45 a.m. when Walter observed something during a routine maintenance climb that triggered 41 years of rotating machinery failure analysis experience. Turbine number 23 was exhibiting blade vibration patterns that weren't immediately dangerous but matched signatures that Dr. Braun had studied during aerospace research into catastrophic rotor failures. The vibration suggested that the composite blade structure was developing stress concentrations that could lead to sudden blade separation, a failure mode that would not only destroy the turbine but could send blade fragments weighing several tons flying over distances that could affect nearby communities. Dr. Braun had encountered similar failure patterns during jet engine development, where rotor blade failures had caused catastrophic engine failures that destroyed aircraft and killed passengers. The physics of rotating blade stress didn't change, whether the application was aircraft propulsion or wind energy generation.
Control room, this is Walter on turbine 23. I'm documenting blade stress signatures that indicate potential catastrophic failure development. Recommend immediate shutdown and detailed structural analysis. Walter, the automated monitoring systems aren't showing anything unusual. The turbine is operating within normal parameters. Walter's turbomachinery engineering training activated pattern recognition that had been developed through decades of investigating rotating equipment failures that had caused industrial accidents, aircraft crashes, and power plant emergencies. Control room, I'm observing blade stress patterns that match conditions that precede catastrophic rotor failures in high-speed rotating machinery. This isn't showing up in standard monitoring because the failure mode develops in frequency ranges that conventional sensors don't detect effectively. Over the next 4 hours, Walter conducted systematic analysis using techniques learned during 41 years of turbomachinery failure investigation. Vibration analysis using portable equipment he maintained for precision diagnosis, blade stress documentation through visual inspection techniques that revealed developing cracks, and performance monitoring that identified efficiency changes indicating structural problems. What he discovered confirmed his worst fears. Turbine 20. Within 72 hours, federal turbomachinery specialists were conducting emergency assessment that confirmed Walter's analysis. The blade stress problems were indeed affecting wind turbines throughout multiple states, representing systematic design and maintenance issues that could cause catastrophic failures affecting entire communities. The investigation revealed that wind turbine blade monitoring systems had fundamental gaps in their ability to detect the specific types of composite material failures that could cause sudden blade separation. Walter's aerospace experience with similar rotating machinery had identified failure modes that civilian wind energy engineers hadn't encountered because their background didn't include the high-stress rotating equipment applications where such failures were well documented. Dr. Braun, how did you identify the blade failure pattern so quickly when our established monitoring procedures didn't detect these problems? Director Kim asked during the emergency investigation coordination. Walter looked across Prairie Wind Energy, where temporary shutdown procedures were protecting communities while permanent engineering solutions were developed. Director Kim, I've spent 41 years studying how rotating machinery fails under stress conditions. Composite blade structures behave according to the same physical principles, whether they're in jet engines or wind turbines. The failure modes are predictable if you understand the underlying material science and stress analysis. The blade safety improvements that Walter's analysis had initiated were implemented across the wind energy industry within 6 months, establishing enhanced monitoring procedures and maintenance protocols that eliminated the catastrophic failure risks he'd identified while improving the reliability that made wind energy a viable alternative to fossil fuel power generation. The story remained largely within engineering publications, protecting both industrial competitiveness and Walter's privacy, while ensuring that wind turbine safety protocols incorporated lessons learned from aerospace turbomachinery research that could complement renewable energy engineering. Walter returned to his wind turbine maintenance duties, serving wind farm operations with the same methodical precision that had characterized his pre-emergency work. But something had changed in his relationship with the renewable energy community and his understanding of how his expertise could continue serving both clean energy advancement and public safety. Dr. Braun, thank you for identifying the blade problems, said Michael Chen, Prairie Wind Energy's operations manager, during the post-emergency analysis. The DOE investigators said your analysis probably prevented multiple catastrophic failures that could have set back wind energy development by decades. Walter looked across the wind farm where enhanced monitoring systems now provided additional safety protection for both equipment and surrounding communities. Michael, I've been working with rotating machinery for most of my adult life. Whether it's jet engines or wind turbines, the physics stays the same. You have to respect the forces involved and understand how materials behave under stress. Were you really an aerospace engineer? Walter smiled, adjusting his wind technician safety harness that covered federal credentials he'd hoped never to need again. I've spent my career making sure rotating machinery operates safely and reliably. Now I get to apply that knowledge to helping renewable energy systems work properly rather than designing military equipment. The enhanced safety protocols that resulted from Walter's intervention became standard throughout the wind energy industry, establishing blade monitoring procedures that prevented similar failures while maintaining the operational efficiency that made wind power economically competitive with traditional energy sources. Dr. Braun continued his wind turbine maintenance work until he was 79 when age finally made climbing 300-foot towers impractical. He spent his final years consulting with renewable energy companies while training younger technicians in rotating machinery analysis techniques that bridged aerospace engineering with clean energy applications. Because he'd learned that the most effective turbomachinery safety often comes from people whose expertise exceeds their visible roles, whose dedication continues regardless of official titles, and whose rotating equipment knowledge serves both individual wind farms and renewable energy advancement with equal commitment, to ensuring that clean energy systems enhance rather than endanger the communities they serve. The wind energy industry's adoption of aerospace-derived safety protocols became a model for how emerging technologies could benefit from expertise developed in related fields, demonstrating that innovation often required not just new ideas, but also the wisdom to apply proven principles from established engineering disciplines to novel applications. Walter's contribution to renewable energy safety extended beyond preventing immediate catastrophic failures to establishing the foundation for long-term industry growth that balanced ambitious clean energy goals with the safety standards that would ensure public acceptance of wind power as a permanent replacement for fossil fuel energy generation.